So we want to talk a little bit about what these types of functions look like once we start considering multiple variables, multiple independent variables. So when we graph an equation in two variables, we only have to think about two dimensions, which in most math classes is what we're used to looking at. Just the x direction horizontal and y is the vertical direction. When we introduce a third variable, now we have to start thinking in three dimensions. So more in the actual kind of real world space that we live in. So for instance, we could start by graphing the point 2, 4. So to do that, we would just find x equals 2 on our x-axis and y equals 4 on the y-axis. So we go to x equals 2 and up to y equals 4 and plot our point. So in two dimensions, we only have to think about how far do we move left or right, and then how far do we move up or down. So now what we want to do is apply this same thinking to graphing a point x equals 2 y equals 4 and z equals 5. So now that we're thinking in three dimensions, we have this three-dimensional plane, which can be a little bit difficult to visualize, but essentially now, instead of x and y being our vertical and horizontal, now z becomes our vertical in this third dimension. So if you sort of look at more of this at a top-down view, we still have x as what was originally our horizontal direction, y which was originally our vertical direction, but now that's kind of flat like a piece of paper, and now coming up out of the paper, we have this new third axis coming up in the kind of third dimension, a new vertical axis z. So in order to graph this, we would go to x equals 2. We would find out where that intersects with y equals 1, 2, 3, 4. So in two dimensions, our point would be right here. But now what's going to happen is this is going to come up out of those two dimensions into a third dimension to z equals 1, 2, 3, 4, 5. So now what we're looking for is where all three of these lines intersect. So right at the intersection of x equals 2 and y equals 4, we would draw a vertical line straight up in space to get to this point 2, 4, 5. So it's always a little bit difficult to draw three-dimensional shapes or plot three-dimensional points by hand. So what we also want to take a look at are some graphs of different types of functions. So ordered triples are plotted in three dimensions, which means that our multivariable functions are also plotted in those three dimensions. So if we have a function like f of xy equals x squared plus y squared, which again we could similarly write this as z equals x squared plus y squared, what we end up getting is something that looks like this cone shape. So since we have an x squared, we start off with something that a general shape of a parabola, but then since it's in three dimensions, that's kind of expanding out and making this cone shape. F of xy equals x squared minus z squared is also a little bit difficult to visualize, but essentially what we're coming up with is something that looks like a Pringles chip. So we have these two curved pieces and then a smaller curve in the center. So we either call that typically a Pringles chip or it kind of looks like a horse saddle, something like that. And then in this last curve we get something that looks kind of like an hourglass shape. Now for our purposes, we don't really have to worry too much about what the graphs of these different shapes look like, but it's just a good idea to get in this frame of mind that now we're thinking in three dimensions. One of the implications of that is that our graphing calculator isn't going to be able to visualize solutions for us like we were able to do with some of the two-dimensional problems before. So the calculus that we've been building on all semester really becomes critical now because we don't have a method with the calculators without doing the actual calculus-based operations to come up with the solutions for the types of problems we're going to be answering.